Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everybody. I hope you all are doing well, and welcome to another episode of Ask Us Anything about electrochemistry. My name is Dr. Alex Peroff. I am an electrochemist at Pine Research Instrumentation, and my colleague Neil is out today. During the summer, we have a bit of a rough schedule, lots of travel, so being able to host these types of live streams becomes a little bit more challenging. Anyway, we host these Ask Us Anything About Electrochemistry live streams on Fridays around 1 p.m. Eastern Standard Time. This is an opportunity for you to ask us any questions that you have about electrochemistry. Now, we've been doing this for a while. I think this is going to be the 58th episode of this live stream. And we have found that in our time doing this live stream, there are several questions that tend to be the types of questions that are best suited for this type of live stream are questions that are kind of in the middle of two spectrums. You can have very detailed questions, very, very specific questions, with which it might be very difficult for me or my colleague to actually answer them. It's like, what's the activation energy for breaking like a C double bond in a very specific molecule? Wouldn't know the answer to that. Similarly, if you have questions that are too broad, like you want a full electrochemistry course, or you want to know everything about cyclic voltammetry, might not be able to do that within the time constraints of this live stream. So that is better suited to attend some of our webinars, some of our YouTube videos. That's a place where you can get more of that type of information. But if there are aspects of your research or a specific concept in electrochemistry that is difficult to understand, then we will try our best to hopefully answer that question. I'll try to go for about 2 hours. That's usually how long these work, or how long we go for, and we'll see if we'll be able to answer these questions. Now, I will say one thing right off the top: Neil is really the expert when it comes to EIS and batteries. I am not nearly as strong in understanding those, but I will try my best to answer your questions about electrochemistry. If you are watching this after the live stream is over, so you're watching this not as a live stream, but as just a regular video, we will have timestamps in the description where you can see the questions that were asked if you're catching up at a later time. So with that said, I think, and also I apologize in advance if I mispronounce anybody's name. So let's just see. It looks like we just have some people saying hello so far. Please also try to make the questions as clear as possible. There are some questions that I have from other people who have asked us YouTube comment questions, and I'll try to answer those too. But I will try to answer questions. Let's see. So Sai Yash is saying hi. This is Yashwanth from India. Hi, Andraha. He's doing. He's a research intern working on batteries, and then he asks how applicable diffusion control. I think I need a little bit more information about what kind of question you're asking. I think I need a little bit more detail. So how applicable diffusion control? One thing to keep in mind when it comes to batteries is a lot of people do think about how do molecules and ions move from one part of the battery to another part of the battery, the anode to the cathode. So some of the materials and the design of the battery, they all move basically via I think it's a diffusion control process, but because of the materials, I mean, you're not using migration or convection to move stuff, but yeah. So anyway, we do have questions. We also have one from X. I will get to Eugene in a minute. So we have a question from Bishnu Chatterjee. I want to perform EIS under OCV condition, so open circuit voltage. So where should I put the OCV value in the Aftermath software? Please help in this regard. If possible, what happens if I do 0 volt condition as default? And then he's saying, or some other voltages, particularly for, I think that's solid oxide fuel cells. So, so this is a great question. I think one thing you can do, and let me actually, I forgot to do this. I should open up Aftermath software so that you will have the ability to see it. So let me share my screen, and I'm going to hide this question. So this is, so hopefully you're just seeing Aftermath software. Let me make sure I am not doing that. I'm going to hide this question for now. All right, so this is Aftermath software. And for doing EIS, and specifically for finding the open circuit voltage in Aftermath, under the Experiments tab here, you should go to Open Circuit Potential. We call it OCP, same thing as OCV. And what you're going to do, you could, if you don't know what parameters to click, you can always hit this autofill button. This just measures the open circuit voltage for about 18 seconds. Sometimes you might need it to go longer, but if you were to perform this experiment, you would hit perform if you were hooked up to an instrument. You would get some data. You would get these lines, and hopefully the line will become straight after a certain point, or it won't move very much on the x-axis. And then when you do electrochemical impedance spectroscopy, EIS, potentiostatic, you can always change between doing the initial settle period, and actually the initial settle period is the baseline frequency. So if I also just autofill these, by default it's set to 0 volts versus OCP. So if it is 0 volts versus the OCP, then it is at the open circuit voltage. Of course, if you have a reference electrode, then you would want it to be versus the reference electrode, or you would change what that voltage is. So for example, if the open circuit voltage was 100 millivolts, you would, and this is with respect to a reference electrode in your system, you would then set the EIS baseline to 0.1 volts versus the reference, because the open circuit potential, that voltage is between, in a 2 electrode system, really your reference on one side and your working. So the potential is measured between the reference electrode lead and the working sense lead on our potentiostats, and for most potentiostats. So the open circuit voltage is that measurement, and you would adjust it to this value, and then you would do EIS, in this case a 10 millivolt RMS amplitude, while doing the experiment. So we even have some options here for checking if the OCP has drifted over time. So there are some things there. But hopefully that kind of helps you with, in Aftermath, how to conduct EIS at the open circuit voltage. All right, Eugene has a question coming from Twitter, from X. Could we talk about Tafel analysis briefly? Yes, I think we can spend a little bit of time talking about this. Not that we have, if there isn't like a very specific question, but generally speaking, Tafel analysis, let's see the best way to describe it or where to go. I think about Tafel analysis from the nature of like the Butler-Volmer equation. So I don't actually have the Tafel equation with me, but I do have let me actually have the Butler-Volmer equation. So hopefully you are seeing this. So this is the Butler-Volmer equation, this guy right here. And when you have, what the Butler-Volmer equation describes is that the net current is equal to a bunch of constants, Faraday's constant, the area, the heterogeneous rate constant. And then it's really looking at the difference between two contributing factors. There is the concentration of your oxidized species, in this case, the oxidant going to plus an electron getting reduced to the reduced species, multiplied by, this comes from the Arrhenius equation, but it's multiplied by this factor, which really is the overpotential, the potential minus the standard potential for this redox reaction. And then you subtract it by the concentration of your reduced species multiplied by, again, e to some constants, but then a function of the overpotential. And so typically what you see in some level of Tafel analysis, let me just get this up so you can see. And I've seen this kind of drawn several different ways, but if you look at it kind of this way, and you're always in a way looking at the absolute value of the current, but I think if you set this to the overpotential, which is sometimes the form eta on one side, and then you have the log of the current. So you've taken the Butler-Volmer equation, and then you've taken the log of it. So actually just going back, if I take the log of the current, and then you have some factors here that are constants, again, and then you have this exponential. The log of the exponential just kind of multiplies it by, it just brings this whole thing down. And all of this gets kind of circumvented into, I should just have the Tafel equation up. Let me actually just try to bring up the Tafel equation. Tafel equation. And then once you see it, so, well, actually it's not even, the Tafel equation actually, I'm just looking on Wikipedia right now, so I will share what I'm seeing on Wikipedia. Let's see, Tafel equation. So when you have the Tafel equation just from Wikipedia, it's what I put. But this equation where the overpotential is equal to plus minus a the Tafel slope times the log base 10 of the current over the exchange current density. And you end up getting plots that look a little bit like this. I will stop sharing. I will share my, let me share just my screen. Useful equations. But you have log of the current, or sometimes it could be the current over the current exchange, or the exchange current. And you end up getting stuff that looks a little bit like this. On either side, it curves a little bit, and then it becomes a straight line. And Tafel analysis and creating Tafel plots, you usually want to, so the current that you're actually measuring needs to be just the current associated with the kinetics of the system. You don't want to have double layer capacitance in it. That's one thing that Neil talks a lot about. You usually want to use a rotating disk electrode to control mass transport during these types of things. But from the Tafel slope, a lot of people are able to kind of look at things like the number of electrons transferred and understand some of the kinetics, ultimately trying to get the heterogeneous rate constant from their species. So if you have more specific questions about Tafel analysis, I think I can go into that more, but I don't have any examples with me right now. So hopefully that's helpful a little bit, Eugene, but anything that's more specific I could get into. Okay, so let's go through. We have quite a few questions coming up. Let's see. What does a higher double layer capacitance mean for an alkaline nickel zinc battery? I don't know. I'm not so sure about the construction of nickel zinc batteries and what that generally means. Usually, if I had to take a guess, Theod, it's based, so the capacitance, the electrical, usually what we refer to as electrical double layer capacitance, that usually comes from electrolyte in your battery, and depending on what electrolyte you're using, you may have different capacitance values based on the ionic strength of your electrolyte, and in some cases even the potential. So there's more capacitance in your battery. I don't know enough about what it means in terms of the performance of the battery. I would imagine it might take a little bit of time for it to kind of charge and discharge, because you need to kind of charge the double layer before any charge transfer processes occur. So that may slow things down a little bit. But again, batteries are not my specialty, so I don't know if that's very helpful. All right. So Sayash asks, how applicable diffusion control in cyclic voltammetry? So to make your cyclic voltammograms diffusion controlled, you need to minimize the other aspects of mass transport. So I have a slide. Go back to these useful equations, but and actually I will not use this. But there's this slide. Let me make sure it's being shared. Yes. So this is the Nernst-Planck relationship, and actually I will hide this and then make this a little bit bigger so everyone can see. So this is what's referred to as the Nernst-Planck relationship. It describes the flux J sub I with distance of an electrode following the following things. So these are all the things that affect the mass transport or the flux of molecules towards the electrode surface. So there's a component associated with diffusion, a component associated with migration, which is the movement of ions due to the presence of an electric field. And there is convection, which I think of as the macroscopic mechanical moving of solution and molecules towards the electrode surface. So for diffusion to be applicable in cyclic voltammetry, only this component can happen or can be the main contributing factor to your cyclic voltammetry data, or the only mode of mass transport. So what is commonly done is to minimize migration, you add a supporting electrolyte. You try to make the solution very conductive. And if you make the solution very conductive, the electric field strength decays very, very quickly away from the electrode surface. So by adding supporting electrolyte and making the solution very conductive, you have minimized how far the electric field moves out into solution. In some cases, you do not have electric fields in conductors. So if you even think about just like a pure conductor like gold or platinum or some metal, it conducts electricity very well. There is no field inside the conductor. And then lastly, this element of convection, mechanical macroscopic movement, you just need to make sure that your solution stays stagnant. It does not move. You're not stirring the solution. And even subtle vibrations can affect your cyclic voltammetry data. So usually some people may even put their electrochemical cell in some kind of vibrationless cage to minimize that effect. That you had to be looking at very, very small changes in the electrochemical signal to see that, or for that to be a big issue. But yeah, when you do those two things, when you don't stir, and then when you have enough supporting electrolyte, diffusion becomes the primary mode of mass transport for cyclic voltammetry studies. So, Sai, I hope that helps you. And then let me at least see. I also want to see if Sai has some other. He says, in voltammetry, so many techniques are available. Why is cyclic voltammetry famous? What factors affect? So I think so just to kind of answer that question. So there are a lot. You are correct. There are many techniques in electrochemistry. And actually, cyclic voltammetry isn't even the best. I think it's become very common. I think part of it has to do with history, but a lot of people use it. It's used not only by electrochemists, but even people who are doing, say, inorganic chemistry. It's much easier for people to, say, scan their voltammograms to look for redox features. But the ability to adjust parameters like the scan rate, just millivolts per second, is very easy as opposed to adjusting, say, the parameters for a step potential technique, like differential pulse or normal pulse. There's so many more variables you need to pay attention to. And arguably, some of these other techniques are better at doing certain calculations. But yeah, CV is famous. It's gotten a hold over the electrochemistry community. It's very well published, and so a lot of people use it. All right, so now going back, let's see. So Fred asks a question. Does RCT mean how hard it is for some electrons to move from one phase, in this case thin film, to the electrolyte? Some of my thin films have almost no semicircle. Some have a visible semicircle. So specifically talking about EIS and Nyquist plots. I just want to see if Fred has any follow-ups. He does have a follow-up question, which is a potentiostat depends on the reference electron set the right potential. Does a galvanostat work in a similar way, or does it just knows what the current... Okay, so that's a somewhat separate question. So let me see if I can't... Yeah, so RCT means how hard the electrons is to move from one phase. I don't know if I would describe it as... let's see, from one phase. Okay, so I don't know enough about your system. Typically, RCT, and I'll just start drawing some stuff to hopefully make sense of everything. So most of the time when you have, like, say, your working electrode, you model it as a capacitor and a resistor. Sorry, can't draw resistors very well. In series. So this is your RCT and this is your CDL. And then you usually have some kind of solution resistance. This is sometimes called RU. But if you have a thin film, so if your electrode, for example, you have a conductive electrode surface, and then you have a film on top of it, right? So you have some kind of film here. Now, I don't know enough about this film, but sometimes every time we have like an interface, sort of say, right, every time we have an interface, we try to model it as what's called a Voigt element. We try to model it as a capacitor and a resistor kind of in series. So sometimes if there's another, so this might be modeled as kind of two Randall's or two Voigt elements in series. The idea being that current needs to flow between like one interface that's here, and then another interface which is here. So that is what sometimes, and we're trying to understand what does it mean RCT in this case. And so I would say that it would represent, RCT does represent how hard it is for electrons to move between your film. But charge transfer resistance usually has to do with an actual, like an electron transfer. So we kind of think about this double layer as no electron actually moves from here to here. There's no charge transfer. We call this a non-Faradaic process. And if there are gaps in spaces, sort of say here, or if there's a buildup of charge on one side and the other, we would model it as a capacitor. But if an electron can move from, let's say, a conductive glossy carbon to, say, some electrochemically active thin film, there is a resistance, there is a charge transfer resistance that we think of or associate with the potential or the energy required to inject, an electron between these two phases. So that's what the RCT is in that kind of situation. So that's how I think about it. That's how I think about RCT when you have these thin films. And so Fred is saying some of my thin films have almost no semicircle, and some have a visible semicircle. One question to ask is, at what potential are you doing your EIS at? Is it a potential where the redox reactions are occurring, or is it not where the redox reactions are occurring? And then let me just see. No follow-ups quite yet. But yeah, so sometimes you can have the same electrochemical system, and if there is so you will not have a semicircle associated with a void with a void element, this RCT, unless a charge transfer process can occur. So if you've done something like cyclic voltammetry on your thin film, again a very popular technique, to see where does the reduction or oxidation reaction occur, if you're not doing it at that potential or near it, you will not see a semicircle. And I've kind of made this mistake several times. But and I'd also zoom in on the Nyquist plot as well. Sometimes you'll see semicircles that are very small. You can imagine that the capacitance between your thin film, between your conductive electrode and your thin film, might be very, very, very small compared to like the electrical double layer. So that capacitance might be kind of overshadowed from one thing to another. So I would look at it. Sometimes you need to zoom in a lot, or you need to, scan to to very low frequencies when doing some of these experiments. Okay, so I'm gonna hide that. All right, so going back, let me move on to the next question, and we're getting. Oh wait, hold on. Fred has a follow-up. So I apply the very small potential 20 millivolts. Yeah, I mean, you might not see anything if that's not, so that may be, so I guess the question is that the amplitude? Is that like the amplitude of your sine wave, or is that or is that only 20 millivolts from your potential to do the experiment? So you're applying 20 millivolts versus your reference electrode and then doing EIS. But you could try, you need to apply enough potential to perturb the system. But if you're seeing some signal, I would look at what your y-axis, if you can see the current data, like a Lisa-Zhu plot, I would look at the current values that you're getting when you apply 20 millivolts. That's one thing that I would do, Fred. Okay, all right, I'm going to try to get to some of these other questions. Okay. Hi, how to correctly integrate the obtained EIS data into chemical reactions? Integrate the obtained. Oh, okay. So, this is very good. Okay, I think I understand what this question is. So if you've obtained EIS data, a Nyquist plot or something, and you've done this for a chemical system, you need to do what's known as circuit fitting. You need to think about your chemical system, your electrochemical system, and model the parts of your chemical system as things like resistors, as capacitors. And then you need to build a circuit model, and there's software that can do this. Our software does this. Let me at least just kind of show you how to get started. Now, I can't fit any data, but I can simulate some data to kind of give you an idea. But hopefully you can see, and let me just see if anyone, okay, so you can't see this right now, but I'm just gonna create a library. Okay. All right, so make sure you can see this up. It's still not being shared. Here we go. So I have created this circuit that you can see on the bottom. Let me just make sure I'm on the circuit. So I created this circuit, and this circuit is supposed to kind of mimic your chemical system in a way. So there's some solution resistance. Maybe you have a charge transfer process, and then you have some double layer capacitance. But within this charge transfer process, there's another kind of void element or charge transfer process that's also possible. So current can go one way or current can go this other way. And based on your Nyquist plot data, you want to ideally fit this Nyquist plot data to your experimental data. And there's a bunch of different things. There's the resistance. In this case, I have, CPEs. I have these constant phase elements, just blanking out on the name, that are representative of the capacitance. So if you can get your Nyquist plot, your EIS data to fit, then you will be able to learn some more information about your electrochemical system. So you can see our tools allow us to kind of adjust or move these around, and depending on what these values are, this will change ever so slightly, depending on what the capacitance is, what the resistance is at these different values. So that's what people do when they're trying to integrate their EIS data into their chemical reactions. They think about their chemical reaction, they come up with a circuit diagram that represents the chemical reaction, and then they try to fit their EIS data to it. Okay, so let's continue. Let's see. Okay, so we have one from Alex. I'm doing a Koutecky-Levich analysis for the hydrogen oxidation, and the Levich constant decreases with increasing overpotential and coincides with the theoretical only at 70 millivolts. And it says, what could be the reason? Is it correct to continue the analysis and calculate the kinetic current if the Levich constant does not coincide with the theory? Well, I think if it doesn't coincide with the theory, there's probably some kind of factor at play. But I'm trying to think about when you say the Levich constant. So there's the Levich equation. Let's see, do I have that on me? Oh wow! Of all the useful equations, I didn't put the Levich equation or the Koutecky-Levich equation in, but I can look that up. Koutecky-Levich equation. I just want to know, when you say the Levich constant, I don't know what that is with regard to. I'm not sure what that is with regard to what you're describing. That's only 70 millivolts. Let me just look up Levich constant. Maybe I don't know. Let me just look up the Levich constant. Okay, so the Levich constant is just, it's just all the things. It's all the things that are not, that is not the rotation rate. So it's just number of electrons transferred, various constant, alpha, diffusion coefficient. So let's see. So in that case, when I'm doing Koutecky-Levich analysis, the Levich constant decreases with increasing overpotential and coincides with the theoretical only at 70 millivolts. I think I need to know a little bit more, like at 70 millivolts versus what? I maybe, okay. Thought it was frozen for a minute. The Levich constant is decreasing. So maybe, Alex, you can just kind of, so it's just talking about the slope of the line. But are you doing this for Levich analysis or Koutecky-Levich analysis? Because I'm assuming the only part of the Koutecky-Levich equation that has to do with this is just involved in the slope, or not the slope, but the y-intercept, because in the Koutecky-Levich equation, which actually I'll just share on here, in the Koutecky-Levich equation, your mass transport, it's all 1 over the current, but your measured current is equal to 1 over the kinetic current from the reactions, 1 over the mass transport current. And the mass transport current is this. So are you just saying that this Levich constant, which really is just indicative of the y-intercept, that this is not the same? And it makes sense that oh no, sorry, I messed that up. This is the y-intercept. Sorry, the kinetic current is the y-intercept, and this is the one that's actually changing. So what you're seeing is, I get it. You're seeing a different slope, and you're seeing a different slope at, and let's see. Okay, I'm getting it now. So you're seeing that. So the slope is decreasing with increasing overpotential. So as the potential increases, the Levich constant is decreasing, which means it's going up. Ideally, it's the same. So for the slope to be, let's see, what would be causing the slope to decrease as you move to? So one thing I'd probably need to look at or know is where are you taking the potential of to get these values. So when you're doing Levich or Koutecky-Levich analysis, let's see. So let me delete all this stuff now. So when you do this, when you have, say, your voltammogram, I'm just going to show you, just one quadrant. So this is voltage, this is current, and then let's say this is 0, 0. And then you start to get this, and you start to get this. And this is your mass transport limiting current. This is the current where nothing happens. And then for Koutecky-Levich, you're really dealing with only the current in this region. So your E naught, let's see. So your E naught, let's say your E naught's around here. Okay. And then only when you move 70 millivolts in overpotential, that's what I'm assuming, that's when you get kind of, you said, like normal-ish results. So he's saying with increasing overpotential, the Levich constant decreases. Let's see. And then, let's see. I'm doing this to calculate the kinetic current, but I'm not sure. Let's see. I'm doing this to calculate the kinetic current, but I'm not sure if it's correct to continue if the slope is not as in theory. Well, I think the slopes, I think there'll be a little bit of deviation in the slope just from experimentation. I would need to know a little bit more about it because, yeah, when I am one of those people who believes that if you're seeing something that deviates from how the equation is supposed to work, you need to rethink a little bit about how it's working. Ideally, the slopes should be the same, but I think it's, let's see, when you're doing the Koutecky-Levich analysis, you're looking at 1 over the square root of the rotation rate, and then you're getting a series of these things as you do it. So I think that, let's see, so it's changing as a function of overpotential. So your slope, so 1 over the slope when you're doing a Koutecky-Levich plot is increasing. Yeah, that's something is a little odd. I may need to think a little bit more about this because that's normally not supposed to happen. And if you think about the things that are in the Levich constant, the kinetic, the kinematic viscosity shouldn't change, the diffusion coefficient shouldn't change, I mean, number of electrons shouldn't change. All those things should be the same. Of course, the accuracy of how, well, I have to think about it a little bit more, Alex. I'm sorry. There are, let's see, does migration, let's see, become a factor at overpotential, perhaps? I don't think so. As long as you have a conductive, enough supporting electrolyte, that should not be. It shouldn't play a role, I think. But, yeah, I guess some of the questions then, Alex. I need to know much more about what your electrochemical system is, so that I can figure out or determine what might be happening and why you might be getting stuff that's not ideal Koutecky-Levich behavior. Also, keep in mind that this kind of analysis really works similar to like Koutecky-Levich and Tafel, and a lot of these. They really work when you have systems with slow kinetics. They don't work so well when you have systems with very fast, redox chemistry. So I have to think a little bit more about it. I might get back to you later, Alex, about what is happening if the Levich constant is decreasing with increasing overpotential. I don't think that is supposed. The Levich constant should be constant. It really should be constant. I think if it's off from the theoretical value, that's okay. That just means something like number of electrons transferred may be something different. But if it's changing, I'm much more concerned about it. You may no longer be in the, quote, mass transport limited region or something like that. Or you may not be in the, quote, kinetically sluggish region. You may be in the mass transport limiting region at that point. All right, I'm going to try to get through as many of these questions as I can. And then if I have more time, I can come back to some of these. All right, Barry, good to see you again. Let's see. What would a Raman spectroelectrochemical setup look like? Is the laser directed at a gold working electrode or a screen printed electrode? All right, very good. So this is actually something I did in graduate school, so I can speak a little bit about it. So generally speaking, there are a few things that kind of have to happen for like a Raman spectroelectrochemical cell. So the type of cell that I used when I was like a graduate student. So this is maybe say the side view of the cell. And if I look on the inside, it kind of had, this was like for a microscope objective. And so my electrode is here. Okay, so my electrode is here, my working electrode. And then I would have ports on the side of my cell. I'd have some ports. So actually there'd be a port here, port here. So, and this is a side view of the cell. And in these ports, you'd have a connection to, say, a reference. You'd have a connection to, say, a counter. And then usually my working electrode was something that I could connect from a wire here. And it would be like a thick thing. And depending on your setup, the Raman laser would come in this way. So your laser is here. You hit the electrode surface and you collect, there's some kind of focusing objective here. So this is a focusing objective. Focusing objective. And so you shine light through the laser, you collect light back, so all the Raman scattered light then kind of converges back. And then usually people have some kind of like a prism, some kind of prism or something that like splits the light. So some of it goes this way, some of it goes through, and your detector is like over here. Your spectrometer and your detector is here. Detect. That is the basic premise of a Raman spectroelectrochemical system. You usually always need to have 180-degree backscattering. Not degrees C, just in degrees. And you collect backscattered Raman light. And you could do that with a traditional, not traditional, but like, a non-screen printed electrode cell, if you wanted to, backscattered. Let's see if I just want to make sure there's any follow-up. So, but yeah, I would focus it on like a working electrode. Screen print electrodes work fine. If you just put a drop of it on a screen print electrode, of your solution, and then shine light on it, do the electrochemistry, you should get some good data. I worked with surface enhanced Raman, so I would have some roughened gold, or I'd have a gold nanosphere type of thing that would help give me enhanced Raman signal. Okay, let's see. What's open circuit potential? Its ideal value should be 0, and if it's not, and if I found it's not, how to incorporate the OCP value during my CV or LSV to get more accurate results? Good, very good question. So the open circuit potential will vary depending on the electrochemical system. And the open circuit potential is the potential, what we say it's the potential at open circuit, but it's basically to say if I had 2 electrodes in solution and I hook a voltmeter to both sides of it, the voltage that I measure between those two, it's the voltage when no current is flowing in your circuit. And granted, a tiny bit of current passes through your digital multimeter, but it's so negligible, it's such a small amount, it's not going to really play a role. So it's the potential difference between, say, a reference electrode and your working electrode. That is what the open circuit potential is. Now, when you put your electrodes into a solution for the first time, they might need time to equilibrate. There's a lot of stuff happening. Stuff that was on your electrode surface might start to come off. New stuff might start coming in. Your open circuit potential, the potential difference between these two, is no longer, is not the same, or it's changing. And the way I actually like to think of the open circuit potential, and this is just, again, kind of a way I like to think about it, is I think of it as based on the Fermi level of 2 electrodes. So I have an electrode, and it's filled up here. This is like full of electrons, and then I have another electrode here that's like, say, full of electrons and stuff. So this is the so this is connected to a voltmeter, and then this is also connected to a voltmeter, and both of these guys are in solution. They're in some water or something like that. Right. So this line represents the Fermi level, which is the kind of the energy where you find like 50% probability that you'll find an electron there. That's one definition. Okay. And when you measure the open circuit voltage, you're just measuring the difference between this level and that level. That's it. And when you put these things into solution, there may be some reactions that, move electrons out of the way, or put they may put electrons into it, or they may take electrons out of it. And so these two levels start to move, and the potential changes. Now, normally, when you have a reference electrode, it's not moving, it's not changing. You've done things to make sure that your Fermi level stays consistent, right? So you have some kind of frit, it's not interacting with the solution very much. And that Fermi level is based on the Nernst equation. So you can govern and kind of manifest, or figure out, not manifest, but you can figure out what that potential is for your reference electrode based on the Nernst equation, and it sticks to that potential. But the potential of the working electrode can change and vary because electrons can move in and out due to reactions of your system. So what does that mean practically when doing an electrochemistry experiment? Most of the time, if you want to find the potential where no electrochemistry reactions are occurring, you're going to want to do something at the open circuit potential and then start your experiment. But most of the time, if you're doing just like a CV experiment, for example, you can step the potential, hold it there for a few seconds, and then start the CV. We have what's known as an induction period in our Aftermath software, and it's 3 seconds. So when you hit go, it moves to a potential, say 0 volts, versus your reference electrode. It holds it there, and then it starts doing, say, the cyclic voltammetry experiment. So this just makes it so that you start with respect, you always want to measure things with respect to your reference electrode. So what you do may change or vary depending on what you're trying to do. Like if I'm doing a CV experiment and I'm constantly changing the potential window around, then how much I care about the open circuit potential doesn't matter that much when doing stuff. So making sure you have a stable reference electrode, much more important. So Samaya, I hope that this is helpful. All right, and let's continue going through. All right, there are several questions coming up. Let's see. All right, I'm going to try to get through these as much as I can. If I can't make it, then I won't be able to. Let's see. Lampner is asking, is it possible to calculate conductivity from a Nyquist plot? In a way, yes. I don't fully. People just ask for conductivity, and conductivity, in my mind, is just the inverse of resistance. And you have something much more valuable. You have the impedance. So what you can probably do from looking at your Nyquist plot is you can take the inverse of the impedance at any frequency and say the conductivity at a specific frequency is the conductivity at that frequency. That's how I look at it. You may find other things. You may use impedance to give you a general impedance value and then take 1 over the impedance to give you the conductivity. But that's my very kind of simple understanding or thought process behind it. I don't know if I can be too helpful because I actually have not done a conductivity calculation from a Nyquist plot, but maybe that's something I will do in the future. Okay. Eugene asks another question. Thank you, Eugene, for asking a question on Twitter. So what's a simple way of explaining capacitance? And what are the impacts of capacitance on battery performance and longevity? So capacitance, or a capacitor first. A capacitor is just a device or a thing where you have 2 oppositely charged parallel plates with a dielectric in between them that prevents charge from passing from one plate to the next. So these 2 plates store charge, negative charge and positive charge, and then there's some kind of dielectric, something that just prevents the charge from passing from one to the other. Now the capacitance in electrochemical systems manifests itself as ions, like supporting electrolyte, salt ions that don't actually undergo an oxidation or reduction reaction, but there is, say, positive charge that moves towards the surface of a negatively charged thing, and they kind of hit each other, but there's no electron transfer. They're just really, really close. Maybe there's a solvent molecule in between them. So that is basically what capacitance is. Now, how it affects battery performance and longevity, I don't know the answer to that. So I have to say I'm sorry. But I will say this. For an electron transfer to occur, for the potential at the electrode surface to be what we say it is, the electrical double layer or the capacitance value has to be at that value. So for example, if you want to apply +1 volt to a working electrode, so say just 1/2 of your battery versus a reference, that 1 volt is based on charge. There's charge buildup. For the charge to build up, an opposite charge needs to come to it to meet it. Like there needs to be an opposite charge that is sufficiently strong to create the voltage that you're trying to get at. So to a degree, I would say that the voltage, and again, of course, I'm not a battery expert, so I don't know this for sure. But I would imagine that the capacitance needs to charge first before you can actually have the electron transfer, the Faradaic process of the electrons moving for a battery to work. So I don't know too much about it, but that's just what I would say. So hopefully, Eugene, that kind of helps. Okay, so Fred has a question. A potentiostat depends on the reference electrode to set the right potential. Does a galvanostat work in a similar way, or it just knows what the current applied is the one that we set? I don't know enough about the galvanostat circuit. Because now the reference electrode, so all these things are based on a feedback circuit. And in a galvanostat, there is some kind of amplifier that just measures the current and allows the voltage to change. So that voltage is being measured, like if you're doing chronopotentiometry, you're monitoring the potential as a function of time. The reference electrode is just another point that helps it, that you're measuring the voltage against. So the working electrode in a chronopotentiometry experiment, the potential will fluctuate versus the reference electrode. The reference electrode still stays what it is. And then the working electrode potential fluctuates to maintain the current between the counter electrode and the working drive electrode in the potentiostat circuit. So that is so that's generally the principle behind it. So so hopefully that kind of makes sense of how a galvanostat works. But some of the circuitry for a galvanostat, it requires a whole bunch of other things that I don't know enough about. But yeah, hopefully that's helpful, Fred. All right, FCB has two questions next to each other. So FCB asks the difference between CV and bulk electrolysis. And then he asks, open circuit potential is kinetic or thermodynamic factors. Best way to choose the open circuit voltage. Okay, so let's go to the first one. So cyclic voltammetry is actually, let me just share my screen. I think this will be fairly easy. You're literally looking at two very different potential waveforms. So in CV, what you apply, this is voltage, and this is time. And in CV, you do this. You're applying some kind of maybe a triangle or several cycles of the voltage. Sorry, I can't draw straight lines. But that's what CV is. In bulk electrolysis, BE, that looks a little bit like an 8, but BE, you are just applying a constant voltage. That's what you're doing. So instead of applying these linear sweeps of the voltage, you're just applying a constant voltage in bulk electrolysis. And what happens when you do that, both experiments in a way measure the current as a function of time, except in CV we report it versus the voltage. But in cyclic voltammetry, we look at the current, which changes as a function of these sweeps. So this is like one sweep. This is this guy here. Let me undo that. Let me highlight this one. So this guy. Let me pick out a different highlighter. So this guy here is this guy here, and then say this guy here is this guy here, and that's just what we observe. So we measure the current, we report it versus the potential that we applied. The current here, as a function of time, spikes. So it has this spike, and then you have this gradual decay in the current over time. So that's what happens when you do bulk electrolysis, generally speaking. So that's the difference between those two techniques. And then you were asking about open circuit potential is kinetic or thermodynamic factor. It's a little bit of both, because the open circuit potential changes, but open circuit potential, once it is stable, then it is thermodynamic, generally speaking. So the open circuit potential is thermodynamic. It looks at that voltage difference, and that voltage difference can be related to, say, the Gibbs free energy of your system. So open circuit potential is thermodynamic. Now, the best way to choose the open circuit voltage is really you want to just observe that the open circuit voltage hasn't changed over time. If the open circuit voltage has changed over the course of your experiment, then that's then it's not very good. And usually some people say, well, I want to make sure that it hasn't changed after 2 minutes. So if it's changed by, let's just say 3 millivolts over 5 minutes, then it's good. It's pretty stable. But if it changes more than that, then the system still needs time to equilibrate. And that in turn is actually a kinetic factor. But really the open circuit potential, once it is set, it should be a thermodynamic quantity. Of course, all things, I guess, in time are thermodynamic. Let's see. There's a little bit of conversation between Chris. Good to always see you, Chris. Thank you for always stopping by. I think, let's see, slip of the line. All right, kind of going back. There's a lot of questions. All right, so this question is from Eugene from Twitter. Thanks for asking this question. Can you explain the difference between square wave voltammetry and differential pulse voltammetry? I can talk a little bit about it. There are subtleties in the nature of the potential waveform, but I actually am not... I understand differential pulse voltammetry pretty well. Square wave is still a technique that kind of eludes me in terms of the difference between them and what you can get. But I will, I'll actually share the, let me just get you to the Pine Research website. Differential pulse. Okay. So hold on. And then do square. Oops. Okay, all right, sorry, I was just getting some stuff up. So differential pulse voltammetry, this is from the Pine Research website. So if you just do a quick search for Pine Research and then type in differential pulse, you'll get this website, and it tells you about differential pulse voltammetry. So in differential pulse voltammetry, you are, I like to think of this as you're applying a normal pulse over a linear sweep or over a linear ramp. You're pulsing the potential as you move the potential up. And so what happens is and it's a differential technique. So you are actually collecting let's see if it doesn't actually have a picture of it, but you are, and actually let me see if I can zoom in a little bit more. You're actually taking the difference between the current, say at like this point, and actually let me just double check to make sure I'm sharing. So let me make this bigger so you can see, and then I'll hide this for the moment. All right, so this differential pulse, and okay, differential pulse. So you apply, you're holding the potential, you step the potential, and you measure a current here, and actually you measure a current here, and you measure a current here, and you take the difference between these two current values. You then step it down just a little bit, again holding the potential. You collect, and I don't remember exactly where you collect the current. I think it's either at this point or it's at this point, but it's the current. So every time you step the potential, you're in a way trying to induce a Faradaic process. And because you're looking at the difference in the currents, if nothing is happening and then you step the potential and again nothing happens, you get 0. So even double layer charging, the effect of double layer charging, the effect of, say, what people call background Faradaic processes, they go away. They are effectively canceled out. However, as you're stepping and continuing to scan, you'll eventually reach a point where your step pulse will actually induce some Faradaic process. And so you get a little bit of current associated with that, more current than before the pulse. And then when you step again, you're going to get a little bit more current, but your background current, you're going to eventually reach a point where, say, your background current starts to incorporate some of that Faradaic component, right? So if I go to, let me now share, let me stop sharing and then share my other screen. All right, so let me delete all this stuff. So if we think about a cyclic voltammogram, for example, in CV, I've got this going on. So, and this is voltage and this is current. So if I think about applying these steps, when I apply this kind of step at this region where nothing is happening, I have very little current here and I have very little current here. And the difference between these two currents is 0. And so when I have my differential pulse, so this is from CV and this is from DPV, what happens is I get like 0 current. I end up getting 0 current because in this region, I apply a potential, I'm stepping it, and then I'm subtracting it from a point where nothing else has happened, so I get 0. The moment I start to get into this zone right here, the current from these steps is actually quite significant. But the current from these steps this is still non-Faradaic. Let's just call this non-Faradaic. No major current passing. And then we start to see current passing due to a Faradaic process. So this is Faradaic. So the difference between these actually results in an increase in the current. So we see this increase in the current. However, when I'm in this region here, what I'll start to notice is I'm actually at a very high potential. And actually at this point, we're still kind of scanning through. But at this point here, the current between here and here is actually about the same. We get to this point where the difference, like this was a point where we had a good bit of Faradaic current, and then we also had the same good bit of Faradaic current. Now this starts to drop off. It slowly starts to go back to 0. We end up seeing this kind of hump. Not a hump, but it's a peak. We end up seeing this decrease in the current because the current at these spots is no longer it's no longer as large. So eventually we're just looking at these differences, and this used to be very big, but then as we keep moving up and up in potential, it doesn't matter how high I step the potential, the difference between the two no longer is that big, and so the current again starts to decrease. So even when we're down in this region where this voltage is here, that's where these potential differences still contain the same amount of Faradaic current, and so you end up getting 0. That, in principle, is how differential pulse works. Now, if I switch and I go to square wave, this is square wave, and it's actually very similar. It's actually very, very similar. The only difference is that there is this narrow, this kind of just like, this is no longer a pulse, but rather it's a longer square wave. It's the same length, sort of say, the duration that the step is held is the same as from the top and the bottom. So I don't fully know exactly, like, I think this is where the sampling period is, but I don't actually know what the main difference is in terms of what new information you get. And maybe it's because you can allow the quote, you remove the charging current from the electrical double layer on your forward and reverse pulse, but you get more information. And this is something that I need to kind of wrap my head around and read some more, like Bard and Faulkner, as to why, like, the main difference between, because really the only difference I see is just how the potential step is, like, one is a pulse and one is just wider. There's a little bit more math that's involved in this. There's a few more equations involved. I think partially because of the fact that, it is, literally half the time when you're doing the forward step. So I hope that's a little helpful. I still need to learn a little bit more about square wave voltammetry and like what's the difference between square wave and pulse in terms of the kinetics and information that you get from it. Okay, I'm gonna try to get through some of these, but Eugene, I hope this was helpful. Okay. All right, moving on. Let's see. Zodiac, yes. Is it possible to calculate the electrochemically active surface area for iridium oxide? I think that's just supposed to be an iridium oxide for the anode in a PEM electrolysis cell. I did a CV, but how do I know where to put my boundaries before the OER peak? Range is minus 0.1 volts to minus 1.5 volts, or to positive 1.5 volts. So I think it's possible. I don't know enough about specifically iridium oxide as the anode. Some people have used the capacitance from the electrical double layer as a way to determine the electrochemically active surface area. I'm not 100% sure if that'll work, but let's just say, for example, if you have this, let's say if we have CV. All right, so you have a CV, and you have a pretty big voltage range, minus 0.1, and then you have positive, I think, plus 1.5. So I'm going to assume it's going to look something like this. I'm a guess. Maybe there's some other stuff that's going on in these potentials. But what I would do is I might focus on this region. I would focus on the region that's just the background current. I would look at a scan rate dependent study, and I'd plot, if this is double layer charging, the current is equal to the capacitance times dV dt, which is your scan rate. And then if you do some kind of linear extrapolation of this, you should be able to calculate what your capacitance is. And once you find out the capacitance in farads, there are some equations, depending on the electrolyte that you're using, there are some equations that say, like, with water, you can estimate like 40, I think it's maybe microfarads or microcoulomb. I think it's maybe microcoulombs per square centimeter. So you might need to do some unit analysis and look up some of these things. This is assuming the dielectric of water. And once you use something like this, you can estimate the surface area, or the electrochemically active surface area. There's several ways of doing it, but that is what you could try doing. Now, granted, I don't know enough about the iridium oxide of your anode and what that does or what it does to your system. But that is one way of doing it. That I hope that kind of helps. Oh, so Alex is getting back to me a little bit. Let's see. So let me just let's see. Okay, so Alex is saying the specification for peak stays within temperature 10 degrees Celsius. How quickly will they break at 2 degrees Celsius? Oh, okay. I don't know. I don't know the answer to that. So you're going to 2 degrees C. How quickly will they break? I'm not so sure. I really don't know the answer. It's not so much like we put these temperature specifications not necessarily because the peak will break or crack, but because of issues with the electrode. So I think, actually, let me take a quick look. I think peak properties. So I'm just going to do a quick look. It's usually known for high temperature, but let's see if I can do temperature. It usually has to do with, oh, I actually can't find the lower temperature limit of this. Well, yeah, I can't find the lower temperature limit of peak, but usually has to do with the interaction between the peak and the electrode material, or the peak with the U cup that's in the electrode. That's usually why we put certain like temperature limits. I don't think the peak will necessarily break, but I don't know for sure. And part of this is also because we don't have chillers that can go to 2 degrees C. So we're not going to say, oh, this electrode can do this thing if we haven't tested it firsthand. So that's that's kind of my caveats about the peak glassy carbon electrodes and what would happen at low temperatures. Okay, there's quite a few questions. Let's see. Oh, and actually Chris has something. I'm always going to give Chris a little bit. What's the difference in COE between... Oh, this is the coefficient of expansion, I believe. I do not know. I would imagine that they would expand and contract pretty... I think they'd expand and contract with each other most of the time. Yeah, I guess. Yeah, I guess. Yeah, we could get more chillers. It's more of the heating is the thing. I guess we could get ice. We could definitely get some ice and do it, but that would be an experiment that right now everyone's kind of at capacity with doing stuff. But that's a good question. Let's see. So let me get to Samaya's question. Koutecky-Levich equation for ORR can used in both kinetic and mass transfer limited region of LSV. In the kinetic region, let's see. In the kinetic region, change the current with increasing rotation rate is small. Although, and I'm trying to see if he has something else. Oh, he didn't say anything. So you cannot use the mass transfer region for Koutecky-Levich analysis. You know, when you have your sigmoid, it's only the region where it's kind of not flat plateaus. So when it's a flat plateau, you cannot use the Koutecky-Levich equation for those regions. And then, so only in the kinetic, quote, sluggish region, as they sometimes call it, can you use Koutecky-Levich analysis. And I would specify it's not just LSV, it's rotating disk, it's RDE, rotating disk voltammetry. And specifically, rotating disk voltammetry at slow scan rates. this is supposed to be a steady state technique. So as you're rotating, you could literally get the same data by holding the potential at each point and then seeing how does it how does it change. We just scan very slowly because we don't want to step the potential. But then you say in the kinetic region change in current with increasing rotation rate is small. That may be the case, but that is okay. It is still changing. There is still a 1 over the square root of rotation rate in Koutecky-Levich, or just square root of the rotation rate change in the current. So it's still important that you see this change in the current, and that's just indicative of your system and the science. So don't feel too bad if you don't see big changes with change in the kinetic region with increasing the rotation rate. That in turn may be very indicative of the kinetic sluggishness of your ORR catalyst, which is important to identify. So hopefully that's helpful. Let's see. How I decide which parameter is important to change the value in aftermath software while doing the experiment. It depends. It depends on what the experiment is. This question is a little bit too broad because there are so many different experiments with so many different types of parameters. So the parameters that when you create a new experiment in aftermath that are yellow, those are the ones that need to be changed, or you need to add values to it. But the autofill button in aftermath should be very good at doing that, or giving you some good parameters. But it depends on what you're trying to do. Sometimes the potential range is an important, is the important parameter to change. Sometimes it's the scan rate. So it really depends on the electrochemical system and what you're trying to do. This guy's asking what's the value of sine 152. I don't know. I would just type that into Google and figure out what the sine is, Abhishek. So I would just do a search on it. But this is not like an electrochemistry question I can help you with. Sorry. Okay. All right. So I'm going to also, I see some people might be spamming. I'm going to just say ahead of time, don't spam the chat, especially if you're asking a bad question. Okay, so next question. What is the difference between the CPE and Warburg impedance? Neil would be a better person to answer this question, but generally speaking, I think a CPE is a constant phase element, and in a CPE, you have the ability to change this alpha factor to make something either more resistive or more capacitive. So it's in a way what we use to model the electrical double layer, and that's what it physically is supposed to represent, this kind of not pure capacitor, but a kind of a fuzzy capacitor, so to say, especially when we have different interfaces where there's charge separation. Warburg impedance is the impedance associated with diffusion, and it's modeled and it operates differently, and it manifests itself very differently. So Warburg impedance usually is, I believe it's a straight 45-degree angled line in the Nyquist plot that just kind of goes out indefinitely for, say, a regular traditional 3-electrode system with a molecule that's freely diffusing in solution. So there are two different things from that perspective, and there's a lot of different math and equations associated with a CPE versus Warburg impedance. So using them, so I wouldn't substitute one for the other. It should be based on the science of your system. Okay. All right. You should. Oh yeah. So you two can talk about your contact information, message each other. Okay. All right. Hi. I have a simple question. What are the applications of CV, LSV, EIS, ECSA, and may I know the difference between them? So they have a lot of. This is a fairly broad question. I'll try to provide some basic things. A lot of these are used for. Well, all these are some kind of electroanalytical chemistry technique. So cyclic voltammetry and LSV are effectively kind of the same. LSV is a single cycle in cyclic voltammetry. EIS is electrochemical impedance spectroscopy. That is when you apply a sinusoidal potential or sinusoidal current to an electrochemical system. You measure the corresponding sinusoidal current or voltage out, and it gives you information about the, in short, the timescale characteristics of your system. And ECSA is just the electrochemical active surface area. So it's not a technique such as the other ones. And cyclic voltammetry is just when you sweep the potential linearly with time and you measure the current as a function of time, but you plot it as a function of the voltage. So some people usually use these techniques like CV and as CV and LSV to look at the kinetics and thermodynamics of a redox process that might be occurring. So if you want to know what your redox potential is, or if you're studying a chemical reaction, a coupled chemical reaction to an electron transfer step, all those things are usually can be looked at and analyzed with cyclic voltammetry, and changing things like the scan rate, for example, in a cyclic voltammogram will help you decouple the kinetics of a chemical step versus an electron transfer step and things like that. ECSA is the electrochemically active surface area. It's just the area of your electrode, and it's the area that is allowed to do electrochemical reactions. There may be some parts of your electrode that are not electrochemically active, and you wouldn't want those to be part of your ECSA. But yeah, sometimes when you're doing experiments and you want to know what the surface area is to normalize your current response, you need to figure out what the electrochemically active surface area is. And EIS is just a much more complex technique. We actually have YouTube videos on most of these, like CV and EIS, that talks to you, that will describe them in much more detail. So I check those out on our YouTube channel. But if you have any kind of specific thing about that, I can a specific question about any one of those techniques, I'll try my best to answer them. Okay, Ashwani's asking, I'm a beginner and I'm using the WaveDriver 200. That's very good. Glad that you have one of our potentiostats. Can you tell me how to start to learn different experiments that is given in Aftermath software? I am become a beginner to pro in Aftermath software. Oh, how can I become a beginner to pro? Fortunately, you just have to use it. Just do some very simple experiments. We actually have an Aftermath tutorial on our website. So let me find that. Give me 1 second. So so we have a Aftermath software tutorial. I'm gonna put this in the chat. So that is that can really help you start learning and knowing some of the tips and tricks with using Aftermath. Also, if you're doing things like EIS, if you're a beginner to electrochemistry, EIS may be a bit too complex right now. But if you But if you're gonna do EIS and you need like circuit fitting stuff, if you're like a tier 2 member of our YouTube channel, Neil has a bunch of webinars that go like a complete 5-part EIS webinar series that not only goes over EIS but also how to use our Aftermath software to do things like circuit fitting. And that's how you really can become like, I guess, a real pro. But yeah, use it a lot. Ask us questions, like a specific thing that you're running into, and that's I think that's the best way. Also, use the manual, like the manual that comes with the potentiostat, like the get started manual, to do things like doing a dummy cell experiment. I would try doing that too. That'll be very helpful. Okay, let's see. So we have this question: does a double layer charging current exist at OCP? So the answer to that is no. There is there may be a double layer. There might be a double layer. There can still be charge at your electrode surface, but a charging current does not exist at OCP, because in a way, actually Chris, sorry, kind of discussed it, right? Talked about it earlier. To measure the double layer charging time of the current, you need to have a changing potential, which is absolutely correct. So the current is equal to the capacitance times dV dt. And if the voltage is not changing, which it shouldn't be changing at OCP, then you're not going to measure a current associated with the charging. That's a very good question. Very, very good question. Let's see. Oh, but he's asking, is it possible to measure the double layer charging because an open seam measurement? I guess, yeah, the answer is no. Yeah, you wouldn't be able to measure it with OCP. So those are all the questions. I think I managed to get through all of the questions, and I'm also fairly a little tired from doing all this. So I think yesterday was the 4th of July, an American holiday. So Neil is out on vacation. There's actually not a lot of people here in the office. But if I answer all those questions, I think that is, I think I'm going to call it a day. Let's see if there are any other questions coming in from anybody else. Well, I'm trying to see. There was one question I wanted to talk about a question that someone left on our YouTube channel. Hold on. Okay. So this is a question at Clark. So he has a system, or she has a system, where there's a very, very low resistance, but they're running into IR compensation problems and solution resistance, even though it's very low, it's 4 ohms. But they have such a large current, and they're trying to calculate the IR drop. So they thought that they solved their problem with IR. And actually, let me just make sure that, yes, everyone can see this. I do IR. Let's see. So I thought I solved the problem with my IR correction, but it turns out I get plots that curves back, which is an indication of overcompensation. I do IR correction by multiplying the solution resistance by the resulting current and subtracting it to the corresponding voltage. For example, if I get 36 milliamps at 0.8 volts versus silver chloride, and 26 milliamps at 0.7 volts versus silver chloride, with 4 ohms of solution resistance, I will have IR corrected values, 90% IR correction, of 0.67 and 0.61 volts respectively. I did this calculation until I get to the lowest applied voltage, where I subtracted the resulting current times RU to the voltage, and I get a plot. The curves back. Am I doing it right? What could be the reason for overcompensation? Even when I use 80% correction, I still get wrong curves. Your help is very much appreciated. Thank you very much. So this is a great question. It's not entirely clear what's going on, but I will say this. One thing that kind of speaks to me in this is this value right here, 4 ohms. How accurately do you really know 4 ohms, especially with passing these very, very large currents? Because 90% of 4 ohms is some small fraction, right? When you have 75%, like I can see if you had 75% IR correction, then this moves this to another value like 3, right? Then you can get 3. But because you're measuring, you have such a small resistance, the difference between 4 and 3 and 2 and 5 ohms will create these huge differences in the applied voltage. Huge differences. So it very well may be the fact, because IR compensation, like this IR correction or 80% IR correction, those two things, that only affects the solution resistance. It's not actually taking this current into account. We're only saying, oh, well, you measured this value, we're going to do 75%, and we're actually going to use this when doing it. So it may very well be the case that you are overcompensating a little bit if you are generating some voltammograms where, let's see if I can draw, but like you get peaks that kind of go backwards and stuff. You have this kind of curve back in these directions. And I would look for, things like peak splitting, stuff like that to kind of help you. Although I can't actually really fathom, like you must have a very large area electrode to be doing CV and getting this. The other thing I would ask is, it sounds like you're doing a lot of these calculations by hand, just doing the calculation to do the correction. I might strongly recommend, and you're taking different points, right? So you're taking a point at 0.8 and a point at 0.7, and then you're doing this correction. As if you're doing this for each data point in your voltammogram, then I think you're gonna get maybe a smoother point here. But I mean, to a degree, I think you really need to have a potentiostat that has IR compensation built in. It ends up being the case that it makes it kind of tough. I mean, when IR compensation is turned on during potentiostat operation, if you actually did the math of taking this, multiplying it, you have done, quote, I would say, one iteration of it. See, when the potentiostat applies feedback, I can stop sharing this. When the potentiostat is applying feedback, it's doing it really, really, really quickly. And it may actually have to do multiple iterations at a specific potential to actually get you the correct amount of compensation when you have IR compensation turned on. And you can, in a way, do this when you think about doing this math. You take the current that you measure, you multiply it, then you feed it back, and then if you actually are doing the experiment and getting a value, you may need to actually take that new voltage that's being applied and then do the same experiment again. Because when you're actually applying that level of compensation, it's adding a lot more voltage to the experiment. And I guess this is just a long-winded way of me saying that I really think you need to get a potentiostat that has some form of IR compensation in it. And even our wave-now wireless potentiostats with IR compensation are not super expensive, and they can go up to like 150 milliamps of current. I might recommend something a bit more powerful, but you can get relatively inexpensive options. So that's just my small comment about it. But anyway, thank you for the question. I'm glad that we're able to do that. Let me look at if there are any updates. Let's see. Answer Pine Research and Crystal. Okay. Yes. Barton Faulkner is a very difficult book to read. Yeah, this book here. Yeah. So the fundamentals are, I also continue to find them very confusing. So don't worry if you're having a hard time like understanding electrochemistry. Barton Faulkner is a good book to have. I might recommend some other books. Actually, there's a simple book called Electrochemical Engineering. And they go through some of the things a little bit easier. I forgot who has it. I don't have the book with me right now. But there's some other books that might be better for kind of wrapping your head around the fundamentals. Okay. I think I'm going to call it right now, mostly because I'm a little bit tired. Normally, Neil has commented that when it's just one of us, it's a lot of talking, it's a lot of stuff going on. But I thank everybody for participating and asking questions. I think this is very good. And next week, I think Neil and I will be here. I will be here next week, but then the following week, I'll be out. And then even the next few weeks after that, our schedule is kind of crazy. So with that said, thank you for joining me, and I'll see you soon.